All right, so what are some things that we learned or recognized or kind of saw in integrating powers of trig functions? Anything that any of you want to mention to help us to kind of approach some of these problems?
Well, I thought one of the neat things from the video was it was talking about how you could basically take out a trigonometric function if it was to a power that was too high for you to use, and then use Pythagorean identities from there to make the issue a little bit easier.
Beautiful. That happens actually quite often with functions involving sines and cosines. One thing to really remember, obviously, is that the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. And that comes in extremely handy in these problems because they are each other's derivatives, which is really nice and handy. Because if I were to take the integral of something like, I don't know, let's say sine to the fourth x times cosine cubed of x dx. Okay. Let's look at a trick that Sean was just telling us. And it's not really a trick, it's just recognizing that if I want to use u substitution here, it would be good to choose maybe u to be sine x or u to be cosine x. But the problem is, if I were to let u be, say, sine x, now I have u to the fourth, and the derivative is cosine x, but then I would have this dx being cubed. So the way that we get around that is that we actually separate off one of the odd power terms. So this one only works if you see one of them as an odd power. So what we're going to do is we're going to rewrite cosine cubed x as cosine squared x times cosine x dx. Now there's a reason why we do that, because now we're going to force that single quantity of sine or cosine to be our du. Which must imply what? So if that's what we're forcing to be u, what do we want u to be? If we want this to be the derivative of u, what do we want u to be?
That thing's integral.
Sine.
We want sine x. Yeah, so we would like u to be sine x so that we could force that single odd power to be our derivative, which is why our du is cosine x dx. All right, well, that's kind of nice, because doesn't that mean that we can now rewrite this as u to the fourth? That's easy to integrate. The problem is that I still see this cosine squared x. However, if I was able to convert this entire part of the integral to one trig function, just a sine of x, then I should be able to integrate it pretty easily. So the tip that Sean noticed on the videos was that if you ever see an odd degree like 3, or in either one of them has to be odd, it doesn't really matter. Okay, if you see an odd power, separate one of those off, and that will become the derivative of sine x or cosine x, depending. Okay, so why don't we go back here and just, instead of rewriting this, let's go ahead and now rewrite this as sine to the fourth x. And now, anytime you see cosine squared x, you should recognize by the Pythagorean identity that that's 1 minus sine squared x, which is what allowed us to convert it into all sine x's. Okay, so the most common trick, I got to stop using the word trick. These aren't tricks. These are the most common method of integrating functions that happen to be powers of trig functions, okay, is to do what we just did right there, is to separate off one of the trig functions. All right, so we're ready to go ahead and now convert this. We can write this as u to the fourth times 1 minus u squared times du. So du was my cosine x dx, u was sine x. So now notice this is nothing more than a polynomial. U to the fourth minus u to the sixth du. Cool. So in using u substitution is one method that works quite often. Just recognize that the only way you can do that is if you separate off a single power of sine or cosine. Okay, it's the only way you can do it. And I guess we could finish up from here. So this is just 1/5 u to the fifth minus 1/7 u to the seventh plus c, which means that my final result is just 1/5, and u was sine. So sine to the fifth x minus 1/7 sine to the seventh x. Cool. So that's one technique, one method that Sean noticed. Thank you very much, Sean. Somebody else have something else that you ended up saying in the videos, or some other interesting things that you needed to remember for these types of problems?
So if it's odd for cosine, you would do the same thing, the Pythagorean theorem. But if both powers are even, then you use the half angle identities.
Okay, so that's the key now. So the only way that we can use this is if one of the exponents was odd. But if it's not odd, then notice the problem. Let's just say that I was to use, we'll just do another one like, let's say, so we got this one. Okay. So now let's look at how this is slightly different if we were to have something like the integral of, how about sine to the fourth x cosine squared x. This is real similar to that last problem, right? The last problem was sine to the fourth x times cosine cubed x. The problem, unfortunately, is the method of solving this is drastically different. This is why integration is so much harder than differentiation. Because there's not necessarily, first of all, set rules for how to integrate certain types of functions. You could change the problem subtly, and the method of integrating is drastically different. That's not what happens with differentiation. When I'm finding a derivative, if it's a product, it's a product. If it's a quotient, then I do the quotient rule. The composition function, use the chain rule. If you throw in an extra exponent, it doesn't really change the method of differentiating. But with integrating, it's drastically different. Okay, so this is where I should probably do a quick little recap of trigonometry, of the half angle identities. Okay. Let me go over here, and I'm just going to remind you of a couple of identities. Okay. There were a couple of identities that we could have rewritten cosine of 2x as. So cosine of 2x. Does anybody remember what that was equal to? How I could rewrite cosine of 2x? The double angle formula for cosine? Anyone?
Yeah, it is cosine squared x minus sine squared x.
You're right. You're absolutely right. It's cosine squared x minus sine squared x. That's one way to write it. if I wanted to write it purely in terms of cosine, then I could just rewrite sine squared x as 1 minus cosine squared x. And then I could rewrite it in a slightly different way. I could have written it as 2 cosine squared x minus 1. Or I could have written it in a different way. If I wanted to convert everything into sine squared x, okay, I could have just converted cosine squared x into 1 minus sine squared x. And the other identity was, get over there. And the other identity here was 1 minus 2 sine squared x. So there were 3 different ways to write the double angle formula for cosine of 2x. Oh, no, there's 1 minus 2 sine squared x. So we're going to focus on both of these, the last two. We're going to focus on cosine of 2x is equal to 2 cosine squared x minus 1. And then we're going to focus on the other one where cosine of 2x is equal to 1 minus 2 sine squared x. So these were the identities that you would have learned back in trigonometry. You would have proven these identities as well and so on. But the whole point of what we want to talk about here is that we're using these the double angle formula for cosine, okay, which is right here or over here. I mean, they're both the same. In order to convert it so that I can now solve by isolating cosine squared x and by isolating sine squared x. So our goal here is to do that. So why don't we do that? So in this case, all I would have to do is I would add 1, then divide by 2. Over here, I would subtract 1, then divide by negative 2. And if I do that, I end up getting a couple of formulas here. I get one formula that says that cosine squared x is equal to, let's do this again, you add 1 and divide by 2, and that gives me 1/2 plus 1/2 cosine 2x. If we do this over here, we end up getting sine squared x. But then look at what we would have to do here. We would first of all have to subtract 1 and then divide by negative 2. And so the only difference here is that now it turns out to be a positive 1/2, just like this over here. The only difference is now we get minus 1/2 cosine of 2x. So what we've done here is we've just created something referred to as power reducing formulas. We've taken cosine squared x and we've reduced the power to where I don't see the exponent anymore. We've taken sine squared x and we reduce the power so that we don't see the exponent anymore. So maybe a lot of trigonometry that just happened there, so I'm going to give you guys a minute to let that sink in, or seconds rather. Anybody have any questions on what we just did in order to derive those two formulas from trigonometry?
I have a different question if that's okay.
Okay.
So like the first problem we did, like integral of sine to the 4th x and then cosine to the 3x, whenever even if there's an even and odd, you focus on the odd, right?
Well, yeah, so if there's an even and an odd, you always focus on starting by separating the odd power into a single power times what's left. So if it was cosine to the 7th x, I would write it as cosine to the 6th x times cosine x. If there was a sine to the 5th x, I would write it as sine to the 4th x times sine x. All you're trying to do is separate out a single power of sine or cosine, which is what you see right there in pink. Okay, but this one down here is a bit different. Okay, so essentially the whole, I guess, method that we have to take here is to reduce, if you ever see all evens, okay, all even powers. So if you see all even powers, then this is where we're going to reduce to single powers of cosine. And if you don't recognize why would we turn to single powers of cosine? Well, let's look over here. Notice how cosine squared x can be rewritten in terms of a single power of cosine. Sine squared x can also be written as a single power of cosine. And so notice that we're going to convert all of the sines and cosines into single powers of cosine. Okay? So we can go ahead and start doing this. A lot of this is just a bit of algebra before we start doing anything. And there are a couple of different methods, I guess, of doing this. But one thing to do is to rewrite sine to the 4th x as sine squared x squared times an extra cosine squared x.
I'm printing it off because I have to have you sign it.
Okay, so sorry about that, guys. So basically what's happening is all you're trying to do is find sine squared x's and cosine squared x's so that I can use the formula. Okay, so this is where we're going to rewrite this as the power reducing formula, which is 1/2 minus 1/2 cosine 2x squared times an extra cosine squared x. Okay. Times what cosine squared x is, which by the power reducing formula is 1/2 plus 1/2 cosine 2x. I like to remember that cosine is just the plus and sine is going to be the same thing but minus. So this is just a lot of substitution here. There's a couple of ways. I mean, there's I don't know. Yeah. Anyhow, this is just a matter of expanding at this point. So if I were to expand this first one, just notice that this becomes, we'll put this in a different color here. When I expand the first time, 1/2 times 1/2 is 1/4. Okay. Minus, and now when I multiply 1/2 minus 1/2 cosine 2x times itself, notice that I'm going to get, well, I mean, I guess you could show the side work over here if you need to do that. Sorry if that printer in the back is a little loud. My wife has to print something off here. All right, so notice that when I distribute here, I get 1/4 minus 1/4 cosine 2x minus another 1/4 cosine 2x, which is minus 2/4 cosine of 2x. So that's minus a 1/2 cosine 2x. I will say that you just have to really concentrate on, give me one sec, I'm sorry. Never mind. All right, you really have to concentrate on your fractions when you're expanding. And then finally over here, you get plus 1/4 cosine 2x. Cosine squared of 2x. Okay. All right, and that's still going to have to be distributed to the other one over here, which is 1/2 plus 1/2 cosine 2x. So these types of problems are just a pain in the ass because there's so much distribution that has to happen. Okay. But here's kind of an issue. It's kind of nice because if you take a look at this first one, notice how I started off with sine to the 4th x way up here, and now I've reduced the power from 4 down to 2. So the key here now is that I've got to still reduce this power right here. Okay, that power. Because now it is a square as well. So I need to rewrite that as 1/2 plus 1/2 cosine of twice that angle. But twice that angle, when I reduce this a second time, is going to now make this cosine of 4x. Okay. I know there's a lot of distribution, so why don't you go ahead and just take a look at what we did there. Everybody okay with that? All right. But I'm not going to do that necessarily right now. I just want to show you that that's eventually what's going to have to happen when you reduce a second time. You can definitely do that. I think it's better to just continue to distribute everything first, and then it's a matter of just simplifying from there, because then you can separate the integral and often do this a little bit easier. So notice that we're going to multiply 1/2. 1/2 we're going to multiply to each of the terms over here. Then we're going to multiply 1/2 cosine 2x to each of the terms over here as well. Okay, so this is just the distributive property. All right, so 1/4 times 1/2, 1/8. Minus, multiply this by 1/2, and we get 1/4 cosine of 2x. Multiply this last term by 1/2, and we get plus 1/8 cosine squared of 2x. So that takes care of multiplying everything by 1/2. Now let's multiply by 1/2 cosine 2x. All right, so if I multiply every one of these orange terms by 1/2 cosine 2x, we get plus 1/8 cosine of 2x minus 1/4 cosine squared of 2x. Hopefully you could see why I didn't change into this form in green yet, because notice that when I distribute, I'm going to be able to combine a lot of terms together to make my life a little bit easier. And finally, we're going to multiply through at the end here to get plus 1/8 cosine cubed of 2x. dx. Just keep in mind, we haven't done anything other than algebra so far. It's just a lot of algebra. So we used up here the power reducing formulas. I'm sorry, right up here. We used the power reducing formulas to rewrite sine squared x and cosine squared x in their appropriate trigonometric form, right? Their power reduction form. But once we did this, this is now just a matter of expanding, just multiplying every term to every other term. Okay. Well, welcome to Calc 2, right? So, okay. So this is now just going to be a matter of simplifying this. Now, when you combine these together, you're going to be able to combine a few of these together. You can combine this cosine 2x and this cosine 2x. You could combine the cosine squared 2x and the cosine squared 2x. And then you've got this extra cosine cubed over here. Now, a few of these are going to be pretty easy to integrate. 1/8 is an easy integral. Cosine 2x is not a difficult integral. When I see cosine squared, though, it looks like I'm going to have to do another power reducing formula, and that's where I mentioned right up here. Sorry, I should go back. 1/8 is easy. Cosine 2x is an easy integral. cosine squared 2x. That's where we're going to have to convert into another power reducing formula. And finally, cosine cubed, that's an odd power, and now I can go back to that prior example and do that. So this is where we're going to go ahead and start to combine and separate. So I'm going to rewrite this first of all as 1/8 dx. I like to separate the integrals at this point so I can focus on smaller, easier, more bite-sized chunks. All right, let's do this. Negative 2/8 cosine 2x right here. Negative 2/8 cosine 2x plus 1/8 cosine 2x is negative 1/8 cosine 2x minus 1/8 cosine 2x. Well, let's pull out the 1/8. I realize that now all we're doing, okay, pull out the 1/8. And all we're doing is integrating cosine of 2x dx. So that takes care of the second one. Now we're going to come over here, and when we combine 1/8 cosine squared 2x minus 2/8 cosine squared 2x, that's negative 1/8 cosine squared 2x. So that's going to become minus 1/8 times the integral of cosine squared 2x. And lastly, we just have this last integral of cosine cubed. And so because it's an odd power, again, I just keep factoring out those coefficients, making this nice and easy. And now you might remember what I'm going to do here is I'm going to rewrite this as cosine squared x times cosine x dx. I just separate off a single power. I know that when I'm writing on here, and at a time I only see 5 of you individuals out of this whole class, so I can't quite tell from where we are, how you're doing. So if there's questions that you have or confusion, or you're like, man, I'm totally lost, you need to speak up and just unmute yourself. Okay, well, I'm ready to start integrating a couple of these, shall we? So let's integrate this one. That's just 1/8 x minus. All right, we can now integrate this next one. Let's do that in turquoise. So if I want to integrate this one, notice that I'm trying to integrate a cosine function, but I have to use u substitution here because this here is a function inside of a function. So if I think of this as being u, okay, then that must mean that the derivative would have to be attached. So I'm going to multiply by 2 by pulling out a 1/2. So notice that now 2 dx is going to be our u. And so we're left with a coefficient of 1/16. And the integral of cosine of the cosine of u du is sine of u. So that's just sine of 2x. All right, that takes care of that one. And now we got to get a little more creative again, because we've got to simplify this right here in order to become the power reducing formula again. So notice that when I'm reducing the power of an even power, I'm trying to do that so that I can integrate just single powers of cosine, just like I did back here. Okay. So why don't we go ahead and just bring down that minus 1/8 and rewrite this as times the integral of 1/2 plus 1/2 cosine of the double angle. Just be careful because the double angle of 2x is now 4x. dx. All right, now since we've already done this last integral, can somebody help me out with how to do that last one? Okay, let's go ahead and talk about how we're going to figure out how to integrate this last one down here. Somebody else help me out with that?
We could use the, oh no, wait, because we have just cosine squared x times cosine x dx. I was thinking that maybe we could use something similar to what we had before, or if not the exact same thing, of that double angle formula. But since it's not like 2x, we instead inside that what we're trying to figure out and expand it. Maybe we could just have the regular one there.
So you're thinking, let's go ahead and use another power reducing formula on cosine squared x and just make it 1/2 plus 1/2 cosine 2x. That would be that's a good thought. The problem with doing that is then I'd have to multiply that by cosine x. And then I'm multiplying a cosine x with a cosine 2x, and I'm not really able to merge those together. Then it'd just get really ugly. So it's a good thought, but not quite. Okay?
You just break it up into 1 minus sine squared x.
That's right. We're going to recognize that the whole purpose of separating off the single power was to make that du. What is cosine x the derivative of?
Sine x.
Sine x.
Sine x.
Which is why what we're going to do now is we're going to, again, just take out that 1/8. And we're going to rewrite this as 1 minus sine squared x times what's left. And the whole point of doing that now for that last odd power, the cosine cubed x, is that now this integrand is nothing more than 1 minus u squared du. Okay, here.
Don't we also have to multiply it by square, or no?
No.
I mean, like by like a 2?
Because cosine squared x by the Pythagorean identity is 1 minus sine squared x. So the purpose of converting that was to turn it into sine x, so that sine x is u. If I let sine x be my u, then the derivative of u is cosine x. That's the reason if you have an odd power that you're actually doing that process. Okay? Don't worry, we're about done. Almost.
My brain really hurts.
I know, as it should. So, let's go back here. We already have 1/8 x. We already have that second term of 1/16 sine of 2x. And now if I distribute this 1/8 back in here, notice that I'm now integrating 1/16, which is nothing more than 1/16 x. And now I'm saying minus, I'm going to take that 1/8 and 1/2 and just write this next integral here as minus 1/16 times the integral of cosine times the integral of cosine of 4x dx. And then over here, this orange one is actually going to be relatively easy because the integral of, I mean, if I distribute this 1/8 into here and I distribute it into here, notice that all we're going to be left with right there is the integral of 1/8 du, which is plus 1/8 u. And then over here, we get minus 1/24 u cubed plus c. Just don't forget the u is sine x. All right, last step here. Second to last step, anyway. Can I just mention, by the way, and as we stop for a second, let's just scroll back up. The reason this is such a challenging problem is because if you look at how many even powers we have two from right. We basically have three even powers. We have sine squared x, another sine squared x, and another sine or a cosine squared x, right? So the point of this is finding the easiest way to reduce this. It doesn't matter how you choose to reduce it, just reduce it in whatever way you can, okay? But because we did that, we're gonna have to use a power reducing formula on sine squared x. Then we're gonna have to reduce the power again on cosine squared x. But then we're gonna have to reduce a third time because we'll have another even power. And that's why way down here, we ended up having to do this other power reducing formula. That was the third time that we ended up having to reduce the power. So you can kind of see from the beginning, whatever the total exponent is, if the total exponent is 6, that means you're gonna have to use 3 power reducing formulas. If the highest exponent is 4, you're only gonna have to, or if the total of the exponents is 4, you're only gonna have to do it twice, okay? So can we start combining a few of these things? Let's go ahead and just write this out one more time here. We're going to integrate this one. We can see that we're going to, same thing we did before, we're going to multiply by 4 so that that becomes du, and therefore multiply the outside by 1/4. Okay. And now this becomes 1/8 x minus 1/16 sine of 2x minus 1/16 x. A lot of these are just dropping down from time to time to time. Now we get minus 1/64. And the integral of cosine u du is just sine of u. Right, so we get sine of 4x. Now down here we get plus 1/8 x. Here we get minus 1/24.
Would that be 1/8 sine x?
Sine x, thank you very much. Be a pity to make a stupid mistake like that at this point of the game. 1/8 sine x minus 1/24 sine cubed x plus c. Holy cow, and we're pretty much done. Okay, the only thing that I would do at this point is combine a couple of terms that are similar, but there's not a whole lot that are similar. And so notice that in this case right here, you could combine the 1/8 x and the 1/16 x. That's it. Notice that you can't combine terms that have a 2x and a 4x, and you can't combine terms that have a 2x and a 4x and an x. You can't combine quantities that are being cubed. So it looks like that's about all we could do. And yes, Brenda, it is very lengthy. And this is Calc 2. So you are going to notice that don't worry, not all of the problems are going to be this long and arduous. I figured it was a good time to discuss it at this point, just because it's, I mean, you might as well do a problem like this during class. Give me 1 second. Okay. There we go. So that's pretty much it. So let's just recap a couple of things. First of all, on an exam, I would never, ever think to do that, entire process with a power of 6 like that, okay? I would also like to demonstrate that there are some ways to kind of get around this. And that's by just factoring out coefficients. So you could have said as well something like, if I were to rewrite this as, let's rewrite that sine to the fourth x as sine squared x times sine squared x times cosine squared x, right? If I were to rewrite sine squared x as 1/2 times 1 minus cosine 2x, and then multiply this again by a 1/2 times 1 minus cosine 2x, and then multiply it again times 1/2 times 1 plus cosine 2x, you might notice that this might make your life a little easier, because then you don't have to worry about the fractions if the fractions seem to be something that's really causing you an issue. Because 1/2, because if I'm integrating this, then notice that I could pull out the 1/8, and now I'm just dealing with non-fraction terms that I could just distribute. So I'm definitely not going to do this whole process again. But the point is, at some point or another, you got to distribute this and reduce the powers. So if it helps to just try to get rid of those fractions by pulling them out as often as possible, then that might end up helping. Okay, just as a little tip. Eric, you have a question? I don't think Eric has a mic, so never mind. Just wanted to see if you could see my messages. Yeah.
Can I ask another question, if that's okay?
Yeah, of course.
So if we had a problem that was like integral sine to the fourth x dx, in one of the videos we've watched, it like solved through how to find the sine reduction formula. Could we use that on the exam, and rather than doing this, or you would prefer us to do it like this?
I want you to use the process of reducing it to single powers of cosine without actually using a formula. So that's why I mentioned, yeah, so don't use a formula. There are some strategies, the formulas that you can, there are no formulas. I don't see any formulas in OpenStax. It's possible that he gave you on a video a formula to reduce those powers. There are some formulas for secant and tangent on 293, but 283. But again, yeah, I'd like you to do this. I will not. The most I will have is 2 power reducing formulas, right? To where you would just have to say maybe sine squared x times cosine squared x, and believe it or not, that would be a much shorter problem. Just just by having one less reduction, that just drastically simplifies the problem. Okay. We're about out. I wanted to mention before we head out, though, that sometimes you'll see some problems involving tangents and secants. Okay, I want to mention a couple of things just to give you some tips. There is a process in, and I could even refer you to the page number. It's page 282. Okay, so if you want to take a look at that, and I'll just write it on here. Page 282. It asks you to integrate secant cubed of x dx. Turns out that this is a really important integral when you're dealing with integrals involving secants and tangents. If you're going to do this, you should do integration by parts. And the way that you would do this by parts is that you would choose this to be the integral of secant x times secant squared x dx. Now, what has a nicer integral, secant x or secant squared x?
Secant squared x?
Definitely, which is why I'm going to let u equal secant x dv equals secant squared x dx, because what is the integral of secant squared x dx?
Tangent.
Tangent x. And then the derivative of secant x is secant x tan x. And then you could go from there. So notice that I just wanted to mention that when you're doing when you're integrating the third power of secant, integration by parts is the way to go. But anytime you're dealing with other secant and tangent integrals, then all you're trying to do is you're trying to find secant x tan x's, because those are derivatives of secant. And you're trying to find secant squared x's, because those are derivatives of tangent. Okay, so as a little example, if I were to have the integral of tangent squared x or tan let's just say something like integral of tan x secant squared x. This is just a very obvious example, but just as an example. Okay, you're trying to find secant squareds so that I could make this u, all the tangents that I see, make them u, and then this right here would be du. So even if you had something crazy like tangent to the 7th x secant squared x, notice because I was able to find a secant squared x, that was the derivative of tangent. So because I was able to find a secant squared x in the integral, this now simplifies down to the integral of u to the 7th du. And then you can go from there. So that's all I got from 3.2. It's, you know, some of these problems do definitely become lengthy, but I figured it's better to do it during class than having to do it in homework somewhere. So if I'm not mistaken, I don't think you really have anything that's too crazy or above power of 4. So that's about the worst that you're going to get.